Okay, so what's up, class? My name is Claiborne Jones, and I am here to teach you about one of my favorite topics in all of physics, waves. All right, waves is a very important phenomena in all of physics for several reasons. It describes many different things that you experience on a day to day. All right, you experience wave phenomena whenever you're able to hear something. Uh, the propagation of sound is described by a wave. Um, the fact that you can even see this behavior is also described by waves. Wave phenomena is just so important that as a guy who grew up in Houston, Texas, um, you're able to describe one of the natural phenomena that you experience throughout the seasons in Houston, hurricane season, using this idea of wave phenomena. Like, so, I just want to say ultimately, waves is a very important topic in physics, and not only important topic in physics, but just important in life in general. But the reason that I want to teach this course is twofold. I want to teach this course, one, because I just find it very interesting. Like I mentioned, I grew up in Houston, so um, being able to understand the phenomena that was occurring around me, I just find it to be, you know, relevant to my life. But the second reason is actually a personal reason. It's a personal goal of mine. My first time actually ever taking a waves course was at UT Austin, at Texas. And it was taught by a professor. Her name was Dr. Sonia Paban. She now teaches at Harvard. So I bet you can imagine how great of a course it was. But um, I actually made an F in that class. Um, and I deserved that F. I didn't go to class at all, and uh, you know, it reflects on my transcript. But um, that I didn't allow that to deter me from attempting to continue to pursue physics. And so after some time, and I came back to it, my second attempt at the course, which was successful, was actually taught by my mentor. His name is Dr. Orange Shindell. He teaches at Trinity University. Amazing institution, personally. Like, if you're looking for somewhere to go, yeah, if you can be taught by Dr. Orange Shindell and the people at Trinity, you're going to get an amazing education. But yeah, it went a lot better. But however, I wanted that top spot. I always aim to be like the best in the class, and I certainly was not able to achieve that mastery of the subject. There was always this one student. They were absolutely brilliant, and I could not reach them. And I tried my best, but I just could not do it. And this was a topic that I really cared for, that I really enjoyed. And I thought, you know, I really want to learn this, but every time I keep failing at it. And so, I guess this is kind of my third attempt at trying to uh, master this subject. And so I figured, all right, well, at first I made an F. I failed completely. And then secondly, I made an A minus. I didn't make that A that I wanted. Uh, and now I was like, all right, well, the only way for me to possibly master the subject is by teaching it. So this is my attempt at creating a course that, one, will serve as an additional resource to the course that I hope to teach in waves in the future to undergraduate and graduate students. And for this course, I'm going to be using the book that I learned out of at Trinity. It's called Vibrations and Waves. It's written by A.P. French. Uh, in the course at Trinity, there was also an optics portion of the course. However, for this course that I'm constructing now, I only wish to teach out of this Vibrations and Waves book. I want to cover the whole thing. So there will be topics in the book that I'm not very versed in, but hopefully by the end of it, I'll be pretty versed in because I've taught the material to you. So I would have had to have learned it by then. But I also want this, like I said, to serve as an additional resource to the students who, when I teach you in the future, whether it be the undergraduate course or the graduate course, if there was ever a topic in the course that I was attempting to explain that I was not able to properly serve you correctly, um, or in a fashion that you were uh, not capable of understanding the message I was trying to relay, maybe this perspective will be able to clear up some of those things. It's just a way for you to be able to get some more help if it's necessary. So, with that, I want to start this discussion of waves. And to say all this, I feel like there's two words that I can use to wrap up, like to summarize the whole idea of vibrations and oscillations. And if you're a very insightful student, I'm certain that you have already figured out what those two words are. Periodic motion. All right, that's the two words. And so I want to start off by defining this thing called periodicity. Okay, so I'm going to define periodicity as a pattern of movement or displacement that repeats itself over and over again. So I'm going to write that, a pattern of movement or displacement that repeats itself over and over again. So a pattern of movement or displacement. Hopefully by this time you get the point, right? A pattern. And if you're not able to understand my handwriting at some point, please comment in the comment section. That way I can possibly clarify, maybe answer the question, or, specify exactly what it is I meant to say. Uh, so, but now that we have periodicity defined, I want to continue the discussion with this idea of a sinusoidal vibration. So I want to imagine a scenario, okay? And actually, I guess we can draw the scenario as we imagine it. So let's imagine that we have some mass system. So some mass. Let's say it's a block for some reason, and it's some mass m. And there's attached to this mass some spring, and this spring has a spring constant, which is k. Okay. I'm assuming that you have some familiarity with what these springs are, but just in case you don't, um, let me write here that the spring constant K is a measurement of the stiffness. So it's a measurement of the stiffness of the spring. Measurement of the stiffness of the spring. This is actually an important point to distinguish that within physics, you have to really be very specific with your word choice on things because things have very uh, tight definitions. And so when I'm saying K is a measure of the stiffness of the spring, okay, I don't want you to go around saying it's the measurement of the strength of the spring. I've made that mistake before. If you do that, you'll be corrected by your advisor. They will quickly tell you, no, it's not the measurement of the strength. The strength is a measurement of when something will break. But the stiffness is not the strength. So I don't want you to make any um, mistake on that. But ultimately, the stiffness is the amount of force that's required to um, stretch an object some unit length. So actually, let's discuss the units on this K here. So K has some units which are force per length. Oh, undo. Gotta get that out the way. Length. And typically in SI, so SI and SI units, force per length is a Newton. Well, Newton meter. Sorry about that. Don't need that. That's a Newton meter. Okay. Well, I guess I could have just put it up here, huh? Newton meter. You gotta bear with me. I'm learning. But anyways, so let's continue our discussion. So I have a question. If I were to take this spring or the spring mass system, and I took this mass and I stretched it, I pulled on this mass some distance. So actually, let me draw over here what I'm saying. I took this mass and I stretched it, or I pulled on it, my mass M, my spring K, and as long as I didn't pull it to where this spring no longer exhibits linear behavior, so as long as the stretch is small enough to where it's still in the linear regime, uh, I would like to describe what the motion of the mass would be. Like how would its motion be described? Well, the way that you would do this is you would label some coordinate system. All right. You want to make some coordinate axes. So you would say, all right, let me label this direction. In this case, we'll say it's X. You could say it's any direction. You could say it's Y, Z, C, B. I could care less what it would be. But in this case, we're going to say X because that's a pretty conventional direction. And so let's say the mass were located initially. So at t equals, I don't know, t before 0. T before 0, the mass was at x equals 0. All right. So this is x equals 0. And then we stretched it. We pulled on it. So at t equals 0, our mass is now located at some x equals a. So this distance here, this distance from here to here, this is some distance a. And then I let go of the mass, right? I want to be able to describe exactly how the mass would behave, like what its movement, what would its motion look like? Well, it'd be one thing we could do is we could simply just record the position of the mass in time, right? So if we just recorded x of t in time versus time, we will see So we said that at t equals 0, right? This is t equals 0 over here. We said that the mass was at some position x equals a. So I'll okay, maybe I'll choose a different color actually. Let's go with green. Some x equals a. And actually, you know what? Uh, I might want to make this smaller. This is the great thing about recording this lecture on the iPad. I can like kind of adjust my drawings. I can adjust my drawings on the fly. So, you know, that's a great thing. And then let's see. So at t equals 0, it was at some x equals a. And now at some later time, it's going to travel to in this direction, right? So after I let it go, after t equals 0, it's going to start propagating in this direction, right? So it's going to now come to some later time and it's going to reach this point, which I'll say is x equals 0, right? It's going to pass through here. I hope that's clear. It passes through here. And then at some later time, it's going to be compressed. It's going to compress the spring, right? And it's going to be at this position. And that position, I'll say is, oops, x equals minus a. All right. So at some later time, it's at x equals minus a. And then at some later time, and then at another time, it's going to go back through the origin. And then it's going to come back to our x equals a. And then it's going to continue to do that. See, once again, great to have an iPad. That's why I did this, because, but maybe on a chalkboard, I would have done it a little better to begin with the first time. Well, that was an accident. LOL. There it goes. All right. See. Then at some later time, it's going to come back to the origin. And then it's going to go back to x minus a. And then back to the origin. And so, the question that I have is, what would this produce? Like, what kind of graph does this look like? So you could think that this graph would be described by some lines, right? You could just connect the points. You certainly could. I see no reason you couldn't just say, okay, well, then the motion is described by these lines, and this would be an accurate description of the motion of our mass. But what you would find, actually, that if you recorded more points and smaller time intervals, so the smaller you made your time intervals, you get a little more accurate description of what the motion of your mass would look like. And you would find that it actually began to look more like a sine curve. And you trace out some sine curve. Let's see here if I can represent that properly. Okay, you'd actually trace out some sine curve. So let's make a guess here. Let's guess at what the position and time would actually be. We could say, and so once again, here's our guess. We would guess that our position and time, x of t, would be some a sine. And inside of here, we're going to say that we have some time variable. But the argument within our sine function has to be unitless. So we need to multiply this time variable by something, by some constant. We'll call it omega. And we'll also add some factor phi naught. And this phi naught is also a constant. It's actually, this phi naught is actually a constant called um, a phase factor. All right, so the reason that we're adding this phase factor is because we need to be able to determine, we could just start our measurements at some time that isn't t equals 0, right? We could have pulled the mass. We could have pulled the mass to this position A, let it go, and it would have begun, and we could have started our time here, started recording once it reached here instead of at minus A, or we could have started recording when it reached x equals 0, right? Or we could have started recording right here or at this point. Our phase factor phi naught would take care of this delay in our recording of the position of the mass. And so uh, let's look at the equations of motion to see if our guess actually describes, oops, yeah, that was an accident. If our guess that x of t is equal to a, some constant a, sine omega t plus phi naught is an accurate description of what the motion of this mass spring system would be. So if we look at Newton's second law, Newton's second law, which says what F net is equal to mass times acceleration, we should be able to determine what the motion of the mass should be, right? That's what this states. This tells us exactly what the acceleration of the body should be. And actually, so now in order to determine this, I would like for you to draw the free body diagram here. You should have some experience doing this. So you should definitely go ahead and make sure you get some practice in doing that. I'll just go ahead and assume that you know how to do such a thing. You know what? Maybe I shouldn't assume because I don't know who my audience is on this video, right? So I won't make any assumptions. In fact, I'll just go ahead and do it. Maybe you don't know. So if we looked at our mass here, just this mass, the forces that are acting on our mass are from the force of gravity, which is acting downward, the normal force, which is acting upward, and depending on where the mass is located, will determine the force at which the spring is acting with. The spring is always acting in the minus direction, the opposite direction of the location of the mass displacement. So for now, I'll denote that there's some force from the spring which is acting in this direction. All right. And so this is the free body diagram for our mass spring, or for our mass system. And it should be pretty clear, or maybe it should be pretty clear that because the mass is not moving up and down, that the normal force will balance the gravitational force. So with that intuition, we should be able to straightforwardly see that the only thing that we really should concern ourselves with here in this case are the forces that are acting in the x direction, which is the force from the spring. And so the force from the spring is denoted as this. So the force from the spring, let me change the color. So the force from the spring, which is acting in the x direction, is equal to, like I said, minus kx, because the force from the spring is going to always be opposite the direction of the displacement, right? If the mass is displaced some distance, click the wrong thing again. It's displaced some distance to the right, the force from the spring is going to be to the left. If the mass is displaced some distance to the left, the force from the spring is going to be to the right. Okay, I hope that makes sense. And so with this now in mind, we know that that should be equal to MA. Now, I need you to recall that A, or rather, let me take a step back, that, that d dt of x of t is equal to the velocity. Now I'm going to define some new notation in which you may not necessarily be comfortable with. This velocity, or whenever you're taking a time derivative of any function in physics, we define that as x dot. So the dot notation, this is the dot notation. And this dot notation means that you're taking a time derivative of whatever it is the dot is over. All right, so the dot is over this x. So I'm saying that I'm taking a time derivative of this thing x, which is, in this case, the position of my mass. And remember, one derivative of that position is called my velocity. All right, so that's my velocity. Now, if I were to take another time derivative, so d dt of dx dt, oops, I put dx dx. We know what dx dx should be, right? It should be 1, right? But the derivative of this should be d v dt. And this is what? This is called our acceleration. Or, once again, using dot notation, this will be x double dot t. Actually, I'm wondering if you're able to follow along in the comment section below. If I wanted to use the dot notation that would describe the acceleration, I keep doing that, the acceleration, how would I represent that using my velocity? Hopefully you were able to understand that question. If you were, comment down below. So x double dot. So now let's go back to our equations of motion from Newton's second law, right? Which says that m, and instead of writing a, we'll write this as, I guess maybe I should even be a little more specific here. Because this is actually what we're going to want to use. D squared x dt squared. So the second time derivative of our position. Is equal to minus kx, all right? And this is our differential equation, which describes the motion of our mass system, which is experiencing the force from the spring. All right, and so with that, I want you to confirm whether or not our guess from the beginning of the class that the motion or the position of the mass would be described by some a sine omega t plus phi naught satisfies this equation of motion. I can give you a hint. So just to start off, hint. Dx of some A, let's say uh, A sine kx plus alpha is equal to a k cosine. Uh, See, man, this iPad thing is amazing, actually. A k cosine kx plus alpha. And then second hint, d dx of, let me see, let's say a cosine kx plus alpha is equal to some minus a k sine kx plus alpha. All right. So ultimately, um, those are the hints that I'm want to give to you to attempt to show that our initial guess satisfies this equation of motion, which I have boxed here. All right. And so with that, that's the first lecture, our first lecture over periodic motion. If there were any questions or any confusion on anything, please ask in the comments. Let me know if there's anything that I can present a little better. Mind you, uh, I accept all critique. I understand it might even be my first lecture, but uh, I could care less. You know, I'm open to hear all comments. Maybe my pacing was too slow. Maybe it was too fast. You know, I want to hear it all. Let me know. You know, maybe I even made a mistake somewhere. If I made a mistake somewhere, please tell me. But I hope that in the future, I grow to be a little more confident in these lectures and it will be reflected. Uh, so, yeah, that's everything for today's lecture. Hopefully, you're able to answer that question. Does our guess x of t equals a sine omega t plus phi naught satisfy the equation of motion here? All right. Uh, Hopefully, it's clear on what to do. And if not, ask ask away in the comments, and maybe I'll post a video on how to proceed. All right, actually no, I am going to post a video on how to proceed. You can find that video in my Instagram. Yes, my Instagram. Yeah, I guess I should say all those things, huh? Yeah, so like, comment, subscribe, and share. Also, follow my Instagram. It's Lord underscore Claiborne underscore Instagram, IG, not Instagram, IG. Like, comment, subscribe, and follow my Instagram. Um, until next time, I'll see you later. Okay. So, yeah, this was fun.